Hello everyone, my name is Hamida Sajjad and this video demonstrates my PDE4431 Coursework 2 Manipulator Simulation. This project simulates a 4-degree of freedom articulated manipulator using Python, NumPy, and Matplotlib. The robot configuration follows the joint order, revolute, revolute, revolute prismatics. This is also sometimes called RRPP manipulator. It provides horizontal reach through the revolute joints and vertical motion through the prismatic axis, allowing the arm to pick objects from floor and place them onto multi-level shelves. The robot, which is our articulated RRP, implements forward kinematics, inverse kinematics, and the entire structure of this program is created based on these two functionalities. Forward kinematics is used to compute and visualize all joint positions, whereas inverse kinematics solves the two-link planar geometry for X and Y positioning and sets the prismatic joint extension to reach the required Z level. The inverse kinematics also includes reach clamping. Whenever a target is outside the workspace, the solver automatically adjusts the position so the manipulator moves as close as physically possible. Now, in this entire program, the code or the structure of this program has been divided into 3 Python files, a README file, and the coursework itself. So this is what the coursework is, and the aim was to understanding the principles of robotic manipulators and to be able to model them using Python. We were given a task to design the robot, which would be able to pick 3 objects from the floor and place them on various positions or various heights on the shelf. Okay, and this was supposed to be done only in simulation, and this is a standard approach in engineering. Whenever we are creating a robot, we have to first be able to simulate it because directly creating a robot can be consuming and expensive. However, keeping in mind, we had to select the DH parameter for our robot, and we had to use at least 4 joints, and one of them should be prismatic. So keeping in all of these rubrics in mind, we have created, at the end, we were asked to upload the GitHub file, which is there in my README, and upload a video on YouTube. So first, let's start about the code and the structure. The simulation consists of a robot model file containing forward kinematics and inverse kinematics, a simulation file, which contains all the UI buttons, object logic, and the animated motion, a full 3D environment with floor objects, shelves, and a home position, smooth interpolation between poses for realistic motion. And the robot obviously contains the forward kinematics, the inverse kinematics, and the positioning of the entire size of my links and everything. So that's how it's done. It has been created as a SCARA style articulated robot to make sure that the geometry and the work envelope is as easy and as supportive as it could be. So what I will do right now is I will run the simulation and show you how the project looks like. So a prerequisite would be to download the NumPy and the Matplotlib already. So while putting the command python main.py on the terminal, we are able to get our simulation open, and it shows how the project looks. So on the left side of the window, there are some interactive control buttons like floor 1, floor 2, floor 3, and the reset button. Each floor button triggers a full pick and place sequence. The robot moves to the object, lowers to pick it, lifts up to a safe height, and moves it towards the shelf. Lowers again, releases the objects, and return upwards. So this has been the entire way the robot is supposed to move. The vertical positioning comes from the prismatic joint, which adjusts to match each shelf's height. The shelves in this simulation are placed at 3 levels, and each object is placed on its correct corresponding shelf. So if I click on floor 1, then it should pick the first object and place it on the first shelf. My shelves in the simulation are placed at 3 levels, and each object is placed on its correct corresponding shelf, like I just said. The entire animation uses smooth trajectory interpolation between IK solutions. So let's try to run the simulation. So when I click floor 1 button, the robot starts the simulation and creates an appropriate position to pick the first object and place it on the corresponding shelf. So it lifts it up to a safe height and it moves towards the shelf. Now it's going to lower, and then finally it releases the object and returns upward. Same thing for the floor 2. The reason the robot goes up is because it lifts up to a safe height. So it understands that this is the maximum reach of my job. So as you can see, all the 3 objects are picked correctly and from the floor. The last one is currently at, and it's going to pick the last object and place it on the shelf. Each object is placed on its designated shelf without teleporting or any errors. The inverse kinematics is correctly handled and is reachable and near boundary targets. The simulation obviously demonstrates a stable RRP kinematic behavior. Then I have a reset button for the home reference. So if I click on the reset, it should take the robot back to the home reference. And this is my entire simulation. So if I talk a little bit about my code, inside the code, I have the robot model and the kinematics, which are the link parameters, which are right here. These are my link parameters, and this is the complete structure of my robot. Then the forward kinematics starts here, and we're doing the entire, we're setting the entire base of the floor and the column and making sure all the angles and the shoulders are correct. Then we're working next on the inverse kinematics, and over here we are using the formula which is obviously given for the inverse kinematics. Same thing was done here for the forward kinematics, and we put it on the code. There's also a joint extension, which is right here. Yes, right here. So this right here allows it to pick and place it on different terminals. Then I have my simulation.py, and over here we have the different, it's been divided into different methods. Each method is targeted into creating different simulations. The first one starts with the robot itself. Then we move on to the home configuration. Then we move to the floor objects, then the shelf geometry, then making sure that we track the objects. Then using matplotlib, we do the figuring, drawing the environment and the robot, making sure the buttons are fixed. This is the code for the buttons. Then making sure the environment is at the default level, which is supposed to be. Then we post it and we make sure the shelf plates are all perfectly aligned. This is the coloring given for them. And then we create the object itself. Finally, we use the animation helper to show the animation that's happening and the pick and place that happens. And this is the pick and place that I was talking about previously. This right here follows this inverse kinematics, the variables that were used. This is the entire README file. which talks about everything that has been done. So this obviously handles all targets with clamping, performs animation and the pick and place with smooth trajectories, presets them to a home button, and that is done through the code self queue home. Sorry, it's right here. That's it. This line right here takes it back to the home position. So the code is all there. This is the README file. Thank you so much for watching this video, and I hope you found the project helpful. Thank you.